Hello everyone, myself Jitendra Dhakar, 5th year research scholar working in the Chemical Engineering Department of IIT Roorkee, India. My topic of presentation is electroviscous effects in the electrolyte liquid flow through heterogeneously charged uniform slit microfluidic device. Electrokinetic phenomena is a family of several effects that occurs in the heterogeneous fluids. The term heterogeneous fluid here means the fluid containing particles or ions. The electrokinetic phenomena generally classified as electrophoresis, electroosmosis, sedimentation potential, and electroviscous effects or steaming potential. Our topic of interest is electroviscous effects. So now we discuss about electroviscous effects in liquid flow through microchannel. When ionic liquid comes into contact with charged surface of the microfluidic device, then charged walls of my device attract counter ions and repel coions, and then rearrangement of the ions formed a electric double layer. That electric double layer is shown here. It is consisting of a compact layer and diffuse layer. The ions in the compact layer are fixed, and the ions in the diffuse layer are free to move. So when the pressure-driven flow is applied in the microfluidic device, the excess ions in the EDL move with the liquid and generates a current that is called steaming current, and the potential related to this current is called steaming potential. That steaming potential drives ions opposite to the pressure-driven flow and generates a current that is called conduction current, and that conduction currents drives liquid with them, and that retarded the primary flow. That effects is commonly called as electroviscous effect. These are some applications of the microfluidic device: biological or chemical reagent detection, point of care diagnostics, DNA sequencing, drug delivery, lab on a chip, and microreactors. Here we can see the representation of drug delivery and lab on a chip microfluidic applications. The understanding of the microscale flow is significantly important for developing the essential and reliable microfluidic devices for these microfluidic applications. Now, problem statement. Schematic of electroviscous flow through heterogeneously charged slit microchannel is shown here. That microchannel consists of three sections: upstream, middle section, and downstream section respectively. Here LU, LC, and LD are the lengths of upstream section, middle section, and downstream section respectively, and W is the half width of microfluidic device. The walls of the microfluidic device are assumed to have heterogeneously charged, where S1 and S2 are the surface charge densities. These assumptions are considered to solve the flow problem. Here flow is steady, laminar, fully developed flow, and liquid is incompressible and Newtonian, and it contains symmetric anions and cations and having equal valencies and equal diffusivities. These are the dimensionless parameter used to solve the flow problem, where Re is Reynolds number, Sc is symmetric number, K is inverse stable line, S1 is surface charge density, and Sr is surface charge ratio. The mathematical modeling used for model the flow problem is described here. So these are the governing equations. Here, equation 1 is a Poisson equation that relates the total potential to the net charge density, and equation 3 is the Nash-Planck equation that describes the conservation of each n species, and equation 5 is the Navier-Stokes equation, that is the momentum conservation equation, and equation 7 is a continuity equation. F is the extra electrical body force term that is shown in the equation 6. These are the boundary conditions for these governing equations. So with the help of these scaling parameters, we non-dimensionalize previous equations, and we will get the dimensionless equation from equation 8 to 11, and the dimensionless groups are shown here. Equation 12 is the current continuity equation. At the steady state, it describes it. At a steady state, it satisfied at inlet and outlet of the microfluidic device, and induced electric field strength is calculated from that equation. These are the computational grid details, and these equations with the relevant boundary conditions are solved using the finite element method based COMSOL multiphysics software. After simulating the flow problem, we get the results in terms of total electric potential, excess charge, induced electric field strength, and pressure fields. Here, total electric potential distribution along the microfluidic device for various surface charge ratio SR 0, 1, and 2, and S1 is equals to 8 and K equal to 3. The lateral curving in the contours of total electric potential occurs due to non-zero potential or gradient is used normal to the wall except as R equals to 0 in the middle section of the device. The absolute value of the U increases with increasing the surface charge ratio from 0 to 2 because increasing in the SR enhances the electrostatic force near the walls that increases the streaming current, further streaming potential. Excess charge distribution for the various surface charge ratio SR equals to 0, 1, and 2, and S1 equals to 8 and K equal to 3. Absolute value of N star minimum increases with increasing surface charge ratio from 0 to 2 because increasing in the SR enhances the charge attractive forces in the close vicinity of the wall that increases the excess charge that we can see in the middle section of the device. Further, the pressure distribution along the microfluidic device for various surface charge ratio SR equals to 0, 1, and 2, at S1 equals to 8 and K equal to 3. The absolute value of the pressure increases with increasing surface area ratio from 0 to 2 because the increasing in the SR enhances the charge attractive forces in the close vicinity of the wall that increases the additional hydrodynamic resistance on the fluid. Therefore, the absolute value of the pressure increases. Excess charge and star variation along the length of the microfluidic device. In the first column of the figure, excess charge is maximum in the middle section when SR is less than 1 because charge on the surface of the middle section is lesser than the other section of the device. In the second column of the figure, the excess charge is uniform in the middle section when SR equals to 1 due to charge on the surface of middle section is equal to the other sections of the device. In the third column of the figure, the excess charge is minimum in the middle section when SR is greater than 1 due to charge on the surface of the middle section is greater than other section of the device. And the absolute value of the N star increases with increasing with decreasing investigative length or ideal thickening. And the absolute value of the N star increases with increasing surface area ratio SR from 0 to 2 and S1 from 4 to 16. Why? Because electrostatic force enhances in the close vicinity of the walls with the increment in the S1 and SR that increases the excess charge. Induced electric field strength variation along the centerline length of the microfluidic device. In the first column of the figure, the induced electric field strength is minimum in the middle section where at SR is less than 1 because the charge on the surface of the middle section is lesser than the other section of the device. And so in the second column of the figure, the induced electric field strength is uniform in the middle section when SR is equals to 1 due to charge on the middle surface of the middle section is equal to the other section of the device. The third column of the figure, the induced electric field strength is maximum in the middle section because the charge on the surface of the middle section is greater than the other section of the device at SR equals to greater than 1. The absolute value of the EX increases by decreasing in the inverse debye length or ideal thickening, and the absolute value of the EX increases with increasing SR from 0 to 2 and increases S1 from 4 to 16. Why? Because electrostatic forces in the close vicinity of the walls increases with the increment in the S1 and SR that increases the available excess charge for transport. Therefore, the induced electric field strength increases. Total electric potential variation along the centerline length of the microfluidic device. The absolute value of the total electric potential increases with the length of the device because clustering of the excess charge obtains due to positively charged surface. And the absolute value of the absolute value of the total electric potential increases with decreasing inverse debye length or ideal thickening, and the absolute value of the total potential increases with the increasing of surface area ratio SR from 0 to 2 and the surface density S1 from 4 to 16 because the charge attractive forces in the close vicinity of the walls increases with the increment in the S1 and SR that increases the induced electric field strength Therefore, total potential increases. The pressure variation along the centerline length of the microfluidic device. The absolute value of pressure increases with the length of the microfluidic device because total potential increases with the length, as we discussed in the earlier slide. That's why that increases the imposed additional aerodynamic resistance on the fluid. Therefore, the absolute pressure increases with the length of the device, and the absolute pressure increases with decreasing investible length or ideal thickening. And the absolute pressure increases with increasing SR from 0 to 2 and S1 from 4 to 16 due to due to enhancement in the electrostatic forces near the wall with increment in the S1 and SR. That increases the total electric potential, as we discussed in the earlier slide. Therefore, the pressure increases. Electroviscous effects measure in terms of electroviscous correction factor. Electroviscous correction factor is defined as a ratio of effective viscosity to the physical viscosity, or the ratio of pressure drop with electroviscous effect and without electroviscous effect. This relation holds good at steady low Reynolds number flow when the nonlinear term is small in the momentum equation is very small. Here we can see the electroviscous correction factor variation with SR at S1 equals to 4 to 16 and K equal to 3 to 9. The electroviscous correction factor shows proportional dependency with S1 and SR and inversely proportional dependency with K, because the pressure drop increases with increasing S1 and SR and decreases with increasing K, as we discussed in the earlier slides. So when the electroviscous correction factor is 1, there is no electroviscous effects, and the electroviscous effect comes into the picture when electroviscous correction factor is greater than unity. So now, conclusion. Poisson's, Planck, and Navier-Stokes equations are solved using finite element method. 4 parameters ranges SR equals to 0 to 2, S1 is equals to 4 to 16, and K equal to 3 to 9. Magnitude of total electric potential, pressure drop increases with decreasing investible length and increasing surface charge density. And the charge heterogeneity affected the total electric potential, charge, pressure drop, and induced electric field strength. And electroviscous correction factor Y increases 31.71% with increasing surface charge ratio SR. So the overall electroviscous effect increases with increasing in the charge heterogeneity. These are the references. Thank you.